is being recorded.
Yeah, you can start.
Okay. Yeah, so like this is the first problem. Let's just define what radin is first. So when, like, let's say you have a positive integer n equal to say p1 e1, p2 e2, some pk ek, right? Then radin is basically defined as p1 p2 all the way to p. It's product. That's radin. This is the definition of radin. Just clarify. Yeah, so like you guys can try this, I guess, for some time. Like this is just like, this is meant to be an easy example just to like get you thinking about what
And we
problems
have
are,
like
how they work.
multiple solutions to it, which are all very instructive.
Oh, yeah, by the way, this problem admits various solutions. So like, feel free to think in many ways. Like any direction you're thinking, there's a very high chance that there is a solution using that. So be open.
Yeah, we can take n prime, sure. So we will have this. What next? Yes, but okay, like okay, I get what you're saying. Right. So the thing is that x to the power x like grows way faster than a polynomial. That's what you were saying, right? Yeah. Yes, this works.
Any other solutions? Like, okay, so like, okay, let's highlight. This is the first idea. Okay, the first idea was f of prime is always p to the power p. Now the reason this doesn't work is because this grows very fast. If you want to formalize this, which will be necessary in a contest because you need to be formal there, I don't think there's any need to do this because that's just overly complicated. You don't need to do that. Like it is basically what we're doing, but you know.
By the way, this notation means that there exists a constant c such that like cx to the power d is like greater than everything.
Yeah, like okay, that's just a very formal way of putting things. Basically, see what are polynomials like? Polynomials usually look like x to the power d plus x to the power d minus 1, something like this, right? With some coefficients, obviously. Right, that's what polynomials usually look like. And if you look at any individually of these, and like let's say x to the power d, for instance, and you compare it with x to the power x, when x is really large, for example, let's say d were say 5, then x to the power 5 and x to the power x. Obviously, when you see x equal to something large, say 1000, this is much larger compared to this, right? That is basically the idea we are using here. A polynomial like f of p, when you take p really large, this will be much less than p to the power p because this grows much faster because the exponent is changing as well, right? The exponent increases as well. Here the exponents are fixed. It's d minus 1, whatever. So this is the first solution approach, let's say. Now
Okay,
there are
so
others as well.
Arav has an idea. So now use a minus v divides v of a minus v of b. But how are you using this?
Yeah, that's also a very good idea. This is also a very classic property of polynomials that m minus n divides p of m minus p of n for any positive integers m and n, which are not equal, obviously.
In fact, there exists like an almost exclusive solution which like doesn't like how do I put it, like we don't even care about the size or something like that. We just spam.
Yeah.
Can we not
Like we
very
said,
even
because-
E2 and stuff and like
Yes, very
radin
good.
is
I think
constant.
Bruce also found the second solution approach. The second solution approach is basically very simple. It basically says that the second approach is f of p to the power k for any k is always going to be p to the power p, no matter what k is. So any prime p you pick and you just vary k, and then for infinitely many inputs, it's fixed. And because it's a polynomial, it follows that it's a constant. But constant doesn't work here. Notice that constant doesn't work because this quantity is not always constant. So there are no such polynomials. So this is the second approach. Okay, very good. Now,
Okay, so-
now on to the third one.
Okay, so I was saying just choose large enough prime p, which is much great. Yeah, that's basically that solution.
Yeah, that's the first approach, right? Size. So we've done size. We've seen like multiple things taking the same value. And now what about 3, the divisibility thing, which is
Yeah,
probably
so-
more number theoretical.
We use what Arav said, but somehow. Can you figure out how? It's actually quite silly. Yeah,
I
Arav.
mean, you don't need large enough primes. You already know that f of 1 is 1 because rad of 1 is 1.
Yeah.
So you don't really need to do that. No, just think about it. Like you need, this is not a very easy constraint to follow for arbitrary functions, right? To have m minus n divides p of m minus p of n.
Okay,
That's
so,
not something any function can always do.
yes, this is also a solution, I guess. But this is quite similar to the second solution.
Yeah, this is effectively the second solution, right?
Yeah.
This is the second solution. It is basically this. P to the power k share the same prime set. So f of p to the power k for all k achieves the same value, and so constant. Which doesn't work because, yeah. Now, so the answer to this, by the way, is there is no such polynomial, obviously.
Okay, anyways, you people have come up with some nice solutions. Let me show you the rather silly solution. So
No, wait, f of 1 is 1. So, no, wait, why do you have p to the power k minus 1 divides p to the power p minus 1? As in, okay, I see. All right, yeah, makes sense. So k divides p. And okay, yes, I think this also works as a solution. Okay. Yes, that works. Yeah.
okay, so the silly solution.
But like, yeah. So now the dumb solution is basically
What's that?
what is f of 2? What is f of 2 going to be? 4. Yes. F of 2 is 4. What about f of say 5?
312.
3125. Now the difference of these two must be divisible by 5 minus 2 equal to 3. Right? So 3 should divide the difference of these two, which is 3121. Does this hold?
But the sum of digits is not
Yeah.
divisible by 3.
Yeah, so this is like classic stuff, right? 3 doesn't divide 312 because obviously. Yeah, so this is the dumb solution. Yes, so like as you can see, this problem has various approaches. There is size. You can do it with size. You can do it that there is multiple points achieving the same value, and you also have some random division thing, which just magically works out. Like not magically, it's expected that some two values would work. Like you might be wondering why 2 and 5. it's not just 2 and 5, like many points will work. For example, like if you just start by listing out, say 1, 2, 3, 4, 5, 6 values, you'll at least find some 3 or 4 pairs among these only which don't work. For example, say 2, 3. No, 2, 3 will work because that's consecutive, but say 2, 6, this probably doesn't work. Or, you can just find out, you'll find many, just include a bunch of other numbers. 2, 5 is probably the smallest one you can find satisfying this. Like the first such pair, some sense. Okay, anyways, yeah, so that's the first problem. Any doubts? Does anyone have any doubts?
Also, please speak up.
Yeah, like if you don't have doubts, say you don't have doubts, so that I know you don't have doubts.
Yeah, it's hard to look at chat.
All right, no doubts. Okay, I'll just say, assume he spoke for everyone and just proceed. Okay, now this particular problem is a bit of a classical result. You should like almost always know this, because this is like, you can in fact treat it as a result in itself, in its own right. It's not really even a problem. It's like something you should know.
And also, you might have seen this problem in some other class,
Yes.
which was in the prerequisite. And even if you haven't seen it, we will obviously tell you again, so it's fine.
Okay, like what is the most confusing thing in this? Probably this, right? How do you deal with this constraint? There is no nice way to deal with that, right? Okay, you know that GCD of f and g is 1, but so what? Yes, precisely, Bezout. But let's get to that. Let's get to that slowly. What is Bezout, first of all? Like, what does Bezout say? Like, first of all, there's Bezout is something that holds over fields which have division defined over them properly, right? Not necessarily fields, also other people, but it's fine. At this point, let's work with the integers. What is Bezout over the integers? Yes, like you guys said Bezout. What is Bezout over integers?
Yeah, tell us what it is. We don't know what that is. Sounds very fancy.
It's not actually fancy. It's basically just like, I wouldn't say it's exactly fancy. It's something, again, it's something you should know rather than anything fancy. It's like, if you're doing numbers here, you should be knowing this. Okay, if m and n are positive integers such that GCD of m comma n is 1 implies what? What does it imply?
There exists a and b such that ax plus by equals 1. Mx plus
M plus bn equal to 1, but yes,
yeah.
that's correct. Very good. So
How do you think it like generalizes into
So-
polynomials?
so how do you think, like, when you go from the integers into integer polynomials, how do you think this extends?
Right.
Correct.
But then does
Exactly.
the equals like
Okay. Yeah, just hold on. So let's say you have f and g, and now you have a and b polynomials such that a times f plus b times g equal to 1. Is this it? Are you sure?
think about it.
I mean, if you're confident this is it, then you should be confident about it.
Also,
Right.
what are the polynomials A and B? Do they have like rational coefficients or integer coefficients?
Yes, that's close. Yes, you can have 2x and 2x plus 1, and then you'll run into trouble because 2 can come over here, right? So you can't have 1 over here. You need to have something else. But what? What other than 2? Yes, we can say some positive number. Correct. Absolutely. You can just say, you can in fact just say any integer. Positive is almost guaranteed because you can just replace a with minus a and b with minus b if you have to. So yeah, we can say af plus bg is some constant c greater than 0, whatever, doesn't matter.
Yes, and as Mayuk says, the polynomials a and b have coefficients, and like they have rational coefficients. So to make them have integer coefficient, what you do is just multiply stuff such that the denominators cancel out, and you will have a constant on the other
Yes.
side.
So Bezout over polynomials basically says that if I have two relatively prime polynomials, f and g, then there exist a and b, which are integer polynomials themselves, such that af plus bg, this polynomial is actually constant. It's a constant polynomial. So it's going to be some fixed integer c. Okay. So we will not be doing a proof right now because the proof follows by, well,
Euclidean division.
yes, it follows by Euclidean division, but it's quite similar to how you do it with like two positive integers. So we won't do that proof here, but let's assume now we know how to deal with this condition, right? GCD of f comma g equal to 1. So let's see how we can use this to get to what we want to do. Right, like, okay, we know that there exists a such that af plus bg is c. C is some constant. Okay, we know there are polynomials like this. Now what? So this condition, we like it has basically converted into this. Now what about this? How do we deal with this?
Okay, maybe if I write it like this, it will help you like realize what it's about. So yeah.
Oh yeah, this might be better.
And n can like increase and decrease. By the way, you all understand what eventually periodic means, right? And what this GCD is. If not, we can just. Okay.
Yes, very good. Bruce has found the correct idea. The correct idea is that GCD of f of n of g of n, it divides what? Both f of n and g of n, right? Now a linear combination of these two, linear meaning like this basically, f and g's linear combination is a of n f of n plus, no, not a of n f of n, rather some constant times f of n plus some constant times g of n. So here when you take any f of n and g of n, you can combine them using this to get c. And you just get that GCD of f of n comma g of n, this value, it divides c, right? Okay, so what? You know that it divides c, that's a very good idea and it's the correct idea. But what now? You don't need to show that it's divide something, you need to show that it's eventually periodic. Meaning if I start writing down these numbers like this, like 1, 2, 4, 1 again, 6, 3, something like that, then eventually after some point I'll see that, okay, 1, 6, 3, 1, 3 is repeating. So it's periodic, something like that.
LCM of divisors of C is just C, right? Oh, S. If it's not constant, then below n of 2 infinity.
Okay. We have a bunch of ideas here, but let's see. Let's go through them one by one. Okay, so the first one says it's bounded, but also periodic modulo any prime divisors. That is true. But so what? it might be periodic modulo any prime divisor.
Yeah, so what Pyro says implies that GCD, okay, like we already have this, but I will just still write.
Yeah. So basically what he says is, but you do need one more technical term to finish even from there on. Like that in itself is not complete, but it's the correct idea definitely.
Yeah, this proves that the GCD is bounded, which is also a cool result and important.
Okay, so the first idea that he pointed out is, okay, so we can say that when you look at this thing, modulo say C, right? It's always less than, okay, divide C actually. Let's say mod C plus 1, anything modulo, any large enough modulo, like, right? So I just look at the terms of the sequence modulo this. Because these are all less than C, sorry, what? We can take
Yeah, I think he wanted to say that if the GCD is not bounded, then you will have large primes and like take prime bigger than C.
no. So
I think this message was about when you want. It's not fully periodic because like
it's
at
possible that the
first-
starting few values because
Yeah,
of some constructional issues. Construction issues meaning I can try to on purpose try to force key for some small values, say from 1 to 10. It is not behaving periodically. I can try to force that by slightly changing f and g and just adding dummy terms to them, right?
the thing is you can control finitely many inputs to be some outputs.
But you can't control everything, right?
Yeah.
If we extend the sequence leftward, it then becomes fully periodic, right? Like f of negative 1 f.
Yes, definitely. Okay, you say that GCD of f of n comma g of n is equal to GCD of f of n plus c comma g of n plus c. How are you going to prove this? Okay. So you're saying the GCD is D. All right, that's a good idea. Assume this to be D, and then you work mod D. So working mod D tells you that D divides this, correct? Now what? So it tells you that D divides this GCD. That doesn't finish, right? It doesn't show these two are equal. It just shows this GCD divides this GCD. Like you're just close. You just have to do one more thing and then
Yeah, we can
follow up very
just go n plus 2c, n plus 3c, and there are finitely many divisors of c. So it can
no. That will not work because here you see you only know that GCD of f of n comma g of n divides this.
Yeah,
Right.
so assume that they are not equal.
Okay.
Then it can only happen for finitely many. Say we take n plus kc. Then
Okay,
it can
so you
only
want to
happen.
continue this 2c,
Yeah.
3c and then it cannot always keep. Okay, yes, that works. But there is a very simpler solution. It is just do it in the opposite way. Let's say the GCD of these two is D prime. Okay. Now D prime must also divide this.
Yeah.
So directly you get that these two are equal. And because these two are equal, it is periodic modulo C. Okay. But your solution works as well. Yeah, that also works. Extended. So did everybody understand the solutions?
Please speak up or at least tell us in the chat.
It's fine. Let's move on to the next problem. Yeah. Have you attached it yet?
No. This is a quite famous problem. It was in, I think, ISL 1997. So you might have seen this before. Yeah, it's in more.
It's quite possible. I mean, everybody takes problems from somewhere, right?
But more importantly, it was in the ISL.
Yes, correct. So
Yes.
it's actually from the shortlist. So it makes sense. It must have been used many places, obviously.
It uses, yes, the idea is right, but can you show us the execution? Okay, so can anyone tell me how do you exactly interpolate?
Yeah, someone mentioned interpolation, but mentioning doesn't always work.
In case you don't know what Lagrange interpolation is, it's like, say you have. Okay, I'll just.
I'll explain that. I'll just tell them this. Okay. Lagrange interpolation. Don't get scared by the beginning. It's actually a very
It basically says that if you have information in n+1 points of a polynomial, then you have the polynomial.
Let's say you have a polynomial p with degree p equal to n. And if I know that p of x is equal to p of xi is equal to yi for 1 less than or equal to I less than or equal to n+1, then I can uniquely find p. Uniquely is the important word here. Uniquely. Okay, that's the important thing here, uniquely, because otherwise it's just a polynomial which works. Doesn't tell you anything about uniqueness. So like, I'm going to explain why you need n plus 1 points. Okay, just to like make you understand. For example, let's say degree of p is 2. So it's a quadratic polynomial, ax square plus bx plus c. Now I told you that I'm going to tell you values of p at some points x1, x2, and x3, right? So when you write out these equations, this is a linear system, right? In a, b, and c. Does everybody agree with this?
Yeah.
So it's just a linear system, right? It has 3 equations and 3 unknowns, a, b, and c. The coefficients of the polynomial are the unknowns because we don't know what it is. And when we solve for these coefficients using these 3 values, we get a, b, and c. So basically, Lagrange interpolation just tells you a quick way, a very quick way to solve this system of equations. Okay, and this is the polynomial. So you might be like, okay, you solved it, but it's so ugly. And yeah, Lagrange we can also prove by linear maps. There is nothing to prove in Lagrange really. See,
I think he means the formula.
yeah, so Lagrange is basically, how do you come up with this formula? Yeah, see, now that's a very
Yeah, it
difficult
just
question, right?
forces the
Because
points to
when
be.
Lagrange, oh, sorry,
It forces the values of y. I mean, the rest of the terms get 0 and only one term is left.
yes, exactly.
Yeah, basically you were constructing says that one thing to like a lot of things vanish in at
Yeah,
some
so like basically Lagrange here just, he got like some, I'm not sure what you need to do to actually be able to come up with stuff like this, but he did. And once you come up with a polynomial like this, it is the unique one, right? Because you can't have other polynomials like this, because if you did, then p and q both agree on n plus 1 points and both have degree at most n. So p is equal to q. So this is unique. The uniqueness follows from this. Is it clear why it's unique?
Okay, we will assume you understand what it is. So the idea is that you use Lagrange interpolation on in the points. You have information for like 0 and 1, and also you have
But there is an important thing I should mention here. The important thing being, we're working in FP here.
and those who don't know, FP just means that the set
FP
of
is basically
residues
the,
modules.
it is basically like this set. This set is FP. Nothing to be very scared about. It's just formal notation for something very simple. This, like the set of residues as in remainders that you can get when you divide by the prime P, that is called FP. That is all that's necessary here in this. So, you know how we have Z of X, R of X, all sets of polynomials. Similarly, we also have FP of X. This basically means that every coefficient is an FP. This means every coefficient is a real number. This means every coefficient is an integer. That's what these mean. So here we're just going to work in this.
And now, and since you can derive information of other points by just these ones, and you have information at 0 and 1 as well, so it makes sense that you want to interpolate with these points. And you have p points here, and it tells you to prove that degree is at most like no, at least p minus 1, right? So it
you
makes
can
sense.
proceed by contradiction. Suppose otherwise.
Yeah, but like it makes sense why it should be at least p minus 1, because you have like,
Yeah, exactly. Yes. Okay, I think I'll let Debayu finish the rest of the proof now.
So first of all, it will be p minus 2 because yeah. So if the degree is like at most this, we interpolate in the at these points. And this expression becomes this f of j product of, yeah, leading coefficient will be 0 because we're assuming this, and we are interpolating with like p minus 1 points. Wait, p minus, no, we are interpolating with p points, right? Because yes, if you have p points,
Yes,
you get
p
polynomial
points.
with degree p minus 1.
P points 0, 1, 2, all the way to p minus 1. These are the points.
So you get this thing. And can someone tell me what the leading coefficient will be of this polynomial?
Just take 1 in that product numerator.
Sorry, I can't hear you.
Take 1 in that product's numerator.
Right. So basically,
Yeah, so basically like each summand in your, like this is sum of a couple of terms, right? So each term is a maximum degree, is of the maximum degree. So, and you just have to sum up the coefficients that each part contributes.
so this is the notation I'm just using for the coefficient of like x to the power p minus 1. And this is nothing but this. Does everyone understand why this is true? And
I
this,
think this might have been a bit unclear. Let me just clarify it again. See, what is the degree of P? P minus, like what is the degree of P?
sorry,
P minus
what?
1.
No, not P minus 1.
Okay.
We are interpolating with p points.
Yeah, the degree of P is actually at most P minus 2 because P is just F, right? P is just F. P is F. P is the same as F.
Yeah, so maximum would be P minus 2.
Yeah. So P minus 1's, whatever, like when you compute the coefficient of x to the power P minus 1 in this sum, it should be non-zero. Sorry, it should be 0. Right? Because the degree is at most P minus 2.
And
So
we're
we are going to,
assuming it.
yeah, we are assuming this, right? It's a proof by contradiction. So we said assume that P is at most P minus 2, F's degree. So then we have this. And now x to the power P minus 1, the coefficient of this must be 0. What is the coefficient of x to the power P minus 1 in this? This, right? Because this x contributes 1, like we've already seen. As somebody
We
has
don't
already
care
pointed out.
about other terms like,
Yeah, this term doesn't matter, no, because it will not contribute to the maximum degree. Does that make sense?
Yes.
Okay, nice.
now
Now.
this we do some computation, which is probably the boring part, but yeah, we have to do. It's like minus 1 times p minus 1 minus j, I think. Yes. And do you see why? Because you're fixing like one thing and you like multiply all of them. So
Yeah,
you'll
I'll
have
just-
j
let's just
factorial
explain
on
this
one
out.
side and
See, you're let's say I is say some k, right? So we're multiplying k minus 1 times k minus 2 all the way till k minus 1, and then k minus k plus 1, k minus k plus 2, so on all the way till k minus n. Does this make sense? We are just multiplying these, right? So this is just k minus 1 factorial. I think this should be j minus 1 factorial, right?
No, the 0 is also used, so it should be j factorial.
Yeah, we have
Yes.
0.
Oh, yeah, my bad. So you'll have k factorial here. And then you have this. This is -1 times -2 all the way till -n minus k, which is
Yeah, which is like p minus j minus 1.
yes, but
And since you will have a negative, you just handle it with this.
yeah.
And to just simplify the computation, this is like stuff you get in this, right? Like p minus 1 choose j. Except you are like dividing the p minus 1 factorial. And you can simply multiply the p minus 1 factorial and it vanishes because, yeah, we have 0 on the other side. So this simplifies to this. And you will have a -1 to the power j as well, because, of course. Does this make sense?
Let me elaborate this part again, because I think people might have missed it. So he basically said that p minus 1 choose j. What is this? This is p minus 1 factorial over j factorial times p minus 1 minus j factorial. Now this particular part of this should basically remind you of this part. We also see it here. So to get this, we multiplied with p minus 1 factorial everywhere. So this part was 0, like he said, so it's still 0. Whereas this part, you just multiplied it with p minus 1, so it becomes this. And this one, which was -1 to the power p minus 1 minus j, he has made it -1 to the power j because p minus 1 is anyways even. P is odd, right? So we're done. Okay. Does that make sense? Yes, j factorial times p minus j minus 1 factorial is the denominator. That's correct.
Okay, so now what we do is we look this mod p. And you can like evaluate it in a nice way. Because there's like p minus 1 factorial. Okay, I will just write the whole thing because why not? Wait. You'll have something like this. We are simply expanding the thing. Okay, wait, it's not p minus 1 minus j, it's just p minus j. There's just computation. Just bear with it. And what can you say about this? Like, this should be something nice modulo p. Like this is -1 mod p, right? Similarly, there's -2 mod p, and there's -j mod p. Yes. Similarly, these are also like, these are equivalent to the above things because this is like j mod p, this is j minus 1 mod p. And after like canceling everything, you will have -1 to the power j.
Right. And now you have this -1 to the power j. It just comes up here. And because this is also -1 to the power j, then product becomes 1. So it just completely disappears. So you get 0 is congruent to sigma f of j.
Can you finish the problem for me?
Yeah, now I think now the problem is pretty approachable. Can anybody do it?
I will just remind you that we have, yes, 0 and 1.
Yes, absolutely. Only 0 and 1, so all need to be 0, all need to be 1. But why is that not possible?
f of 1 is 1 and f of 0
Right.
is 0.
Exactly. So that finishes. Yes. So that was this problem. Now, I hope this is clear to everyone. Does anyone have any doubts on all of the steps we followed?
Okay, so now you have a choice. What problem do you want to do? Do you want to do this problem which says, okay, you have the P set, right?
No, I never sent.
No, Archit, do you have the P set?
Yes, I do.
Then can you just screen share and let people choose what they want?
Okay. Okay, so we just did 1, 2, 3. Now you guys need to choose which one among 4, 5, 6, 7 do you want to do? There is some poll option, right? I think Zoom has that. Can someone implement it? There are only 15 people, so it might not be the best way to decide.
Yeah, just write it in the chat, like what problem.
Yeah, just write in the chat. We'll find out which one is most frequent or frequent. I should have let them. Yeah. Okay. We have 6, 7, 6, 6. Okay, 6 seems to be winning. One more 6. All right. 7. All right. Some people want to do 7. 2 people want to do 7 so far. Another 6. All right. All right. So we have a lot of 6s and 2 7s so far. Is that how it is? I guess nobody liked 4 or 5. Okay, that is true. 5 is sure. That is true. All right. I think the voting can be assumed finished now. So let's go with 6. Right. Just let me just put the problem. Okay. Okay. I think I read some idea like f of b to the power I is b to the power j. Now, that is an absolutely correct idea, but first let's let everyone try it maybe. let's keep this here. Yeah. All right. So what does the problem say? The problem says that B is some positive integer. You're working in base B. Oh, I forgot to mention here B should be greater than 1. Otherwise, a lot of things don't make sense. Just that. Okay. Now we have SB of n equal to SB of f of n. Basically, sum of digits in base B is equal for n and f of n. Okay. Does everybody understand the statement? Okay, I'm sure there shouldn't be any difficulty in understanding the statement. Yeah. Now, what ideas do you have? Like, what can we try here? Okay, first of all, what do you think the solution set should be? Like, what is the solution set going to be?
Probably like some power of B times the number.
Yes, very good. B to the power L times n, something like this. Right? Why? Because in base B, this B to the power L basically just becomes zeros at the end. Right? Yes, exactly. XB to the power K. B, K is fixed. Okay, let's go back to the idea that was given earlier. Let's, in base B, some amount of zeros, and then B. What is this number? This is basically some B to the power K for some K. So what is SB of B to the power K? What is this going to be? 1. Yeah, exactly. This is like a no-brainer. It's obviously 1. And when is SB of some number U equal to 1? When does this happen? Yeah, only for B to the power K. So this is an if and only if condition. SB of U is equal to 1 if and only if U is of the form B to the power K. Right? So if we plug n equal to B to the power I for some I, then f of n will also be some B to the power J. Make sense? So what I basically know now is that SB of n equals SB of f of n. So if I just plug n equal to B to the power K, I get SB of B to the power K, which is 1, is equal to SB of f of B to the power K, which means that f of B to the power K, this thing, is always of the form B to the power U. So we'll just say U as a function of K. So UK, some sequence, right? As you go K equal to 1, 2, right? So U1, you'll get some U1, U2, and so on as well. Does that make sense? Okay, yes, we have a couple of correct ideas, size ideas, I would say, which are correct. But Okay, if you have another idea of periodic valuation. Okay, how do you want to use periodic valuation?
So like assume the coefficients are a1, a2 till an,
All right,
and then
ANX then like this.
yeah, the
All right.
standard.
All right, this is the polynomial f. Okay, go on.
And then suppose that we check the exponent of b in each of the coefficients, and like I wanted to say that let write an equals some bn times b to the power alpha, like take the highest exponent out of b from each coefficient. No, like
You're saying
right.
something like set x equal to b to the power alpha.
Yeah. First I'm saying that let an equal to bn times b to the power alpha n. Like take the power of b out from an.
Sorry, what do you mean?
Like an equals some bn times. No, don't
Okay,
take
I
bn.
get it. All right, got it. B to the power L times some number, right?
Yeah, like that.
You want to
And
call this Bn?
yes, bn is a bit confusing, so take cn.
Yeah, exactly. That's what I was confusing. Cn. All right.
Yeah, and then for some large, suppose we take some b to the power k as our x,
Okay.
and the highest power of, basically I wanted to show that
Yeah, you're trying to say that this should have most of the B stuff. So if I just factor out the B stuff from here, this stuff should not even exist.
yeah, like that only, or
Right.
it exists.
I get that. All right. I got the idea. Yes. Okay. Okay, fine. You say that you're going to set n equal to some b to the power
Some
k.
large number.
Yeah, some large k. Fine. Look at this. You'll get something like this, right? N minus 1k plus
Yeah.
n minus 2,
So
something.
I basically wanted to
Little a naught.
differentiate all the powers so that b doesn't divide this whole expression.
Yeah, but b can divide this whole expression. For example, a naught could be
Yeah.
divided by
If
b.
it divides, then there are infinitely many terms such that, suppose that a naught equals b to the power some alpha.
Okay.
And as there are infinitely many values of k we can take, so suppose a naught equals, for example, b to the power 5. So for infinitely many terms, it would be b to the power 1 or b to the power 2 or b to the power 3, like that. So it should be constant.
Yes.
Sorry, I'm
This will
unable to
work.
explain my idea very
No,
well.
I understood. This works. This is okay. This is correct. See, basically what he's trying to say here is you have a n xn plus a n minus 1 x minus 1 plus dot whatever all the way till a naught, right? Now what you will do, you will set x equal to b to the power k and you will keep increasing k. Okay. So eventually in the long run, the power of b that this has will increase beyond this and all of these. It doesn't matter how much an or an minus 1 has because k is becoming infinite. There is a very easy proof for this. An, let's say, is of the form like we've already seen b to the power ln, let's say, right? Ln. So ln plus kn is the power of b in this.
Yeah.
Because
So
from x you'll get b to the power k. And from the other you have some li plus ki. Right?
yes. So if
You
we
just want
take
this.
large enough, then it will work.
Yeah, because n is larger than I. When you take k large enough, it will work. So he has basically shown that this thing will have very, very large power of b dividing it compared to these people.
Yeah, and we
Which
want
means that
all of
when you
them to be
take
distinct.
VB, okay, one problem here. B is not a prime, so VB is not defined. How do you want to go about this? This is a dumb issue, but still I'm just bringing it.
Choose a prime dividing B.
No, you don't have to do that. You can just extend the map B to prime to non-primes as well. Define
Yeah.
VB as the same thing, but largest power dividing. No need to consider primes. Just extend the map. You can do that. And it
Yeah.
still satisfies some of the basic properties here. Okay, all right. So what does this tell us? This tells us that VB of this will become what? Just the
So it
smallest.
basically tells us that these a1, a2 till an minus 1 are 0.
Yeah, no. This will actually force that VB of this and in the long run is just L naught.
What is L naught?
L naught is like you defined. An is B to the power Ln times Cn, right?
Okay.
Yeah, so L naught is the power. So VB of this thing when n is large enough will just become L naught if this stuff exists. The only problem arises, it arises when all of these are not there. None of this is there. And that is the only possibility, because otherwise some AI exists and you'll have Li, and then this is too small now because UK will keep
Yeah.
increasing. Okay, so this is basically a size idea, but you have hidden it using B to the power like VB and all that. What you can instead do, which was also pointed out, you can just f is polynomial, so UK needs to be linear in K. To make that more precise, what he's saying is, see, f of x, there is something very special about f of x. Let's say it is some an, xn, whatever, right? So if you look at the limit of this as x tends to infinity, this is an. Does everyone agree? Are there any doubts in this? Makes sense, right? Because when x is really large, these terms, they don't matter compared to this, right? Because you're dividing by x to the power n. So what, let's say an minus 1, x to the power n minus 1 was here. When you divide by x to the power n, what does this part become? It becomes an minus 1 by x. When you divide by x to the power n. And when you take x large enough, 1 by x takes this down to 0. So in the following terms, similarly, they're all 0. So in the end, the only thing that remains is an. Right? So we know that there is some C and D such that this is 1. Remember, I've written C here as well, so the constant is already included here. Is this clear? I think this part is clear.
Yes.
Okay. Now, similarly, if I just do k tends to infinity and f of b to the power k over c times b to the power kd. This is also 1. It's basically the same thing, but now k is increasing, so b to the power k is increasing to infinity. Make sense? All right. Now, what is f of b to the power k?
B to the power j for some z.
No. It's a sequence, right? B to the power uk, like we've already written here.
Okay.
Yeah, we defined this, right? This thing, this part. So yeah, what is this doing here? Anyways, yes, so you have b to the power uk over cbkd, limit k tends to infinity is 1. Let's just push this c here because I should not have even done that in the start. So you have this. So this becomes limit k tends to infinity, b to the power uk minus kd is equal to C. Right. What does this tell you? Oh, come on, like I have some sequence and then I have this limit u tends to infinity, b like something to the power something. And so what is going on here?
Yeah, like they should be the same.
Not the
UK
same,
equals KD.
UK
not
must also
exactly
tend
the
to
same.
infinity.
You just take logarithm both sides. So you get limit k tends to infinity, uk minus kd is equal to log bc whatever. Okay. This is something, doesn't even matter.
Yeah,
So you have
non-stream
something like
maybe
this.
some constants.
Yeah, some constant d. No, d will be a repeat, sorry. Let's use some different name for this. Let's say k. Okay, this is a test of endurance. When will we find the first variable we have not already used?
E.
No, but e is e. We don't use e.
F.
No, f doesn't look good. You have to be aesthetic as well.
G.
No, that's just even more ugly.
Take I.
Let's go with p. I think p we haven't used. I think we will be safe with p.
But P stands for primes.
But we're not using any primes here.
Okay.
Guys, don't worry. This is the same guy who says EGMO as EGMO and stuff. He even pronounces like INMO as INMO.
Anyways, ignoring that comment, we have uk equal to kd plus p for large enough k because the limit is p. Does that make sense? Now remember, what was uk? uk was defining this, right?
Yeah.
So you get b to the power kd times b to the power p, which is just c. Remember that. This is equal to b to the power k, f of b to the power k. So
Yeah.
this is basically cx to the power d.
For infinitely many B, so
Yeah, for
we are done.
infinitely many x. Exactly. So what does this tell you? F of x is equal to
B to the power some L times X to the power D.
just cx to the power d, right? Something.
Yeah.
Okay, now what? What about c? Do we know anything special about c?
Yeah, it's B to the power L.
Yeah, exactly. Because p is an integer, so it's also b to the power p times x to the power d. So we know that f of x is b to the power p times x to the power d. Now what? We are still not done. You just
Yeah, we
found a
need to check
polynomial.
it.
We have to show that this works, or maybe does not work because d cannot exist, something. Really? B to the power p times x to the power d works. Okay, first of all, we can do SB of f of x is always equal to SB of x to the power d, right? We can completely ignore the b to the power p part because that is just going to be a bunch of zeros at the end. Agreed?
Yeah. So maybe D is only equal to 1.
Yes, but how do you show that? I think Prithviraj has an idea on this. We plug powers of b plus 1 or b minus 1. All right. So how does that help? See, right now we just have to check SB of n is always equal to SB of n to the power d. We just have to find all d for which this holds. Right. That's it. This is all we have to solve now. Every polynomial stuff is gone. This is just this now. Okay, Pyro has an interesting idea. He says, you're saying to plug n equal to what? B to the power k plus 1. All right. Cool. So what is SB of n? 2. Yeah. So this is also 2, which means this is also of the form b to the power k plus 1 for some other k, obviously. So you have b to the power k plus 1 to the power d is equal to b to the power l plus 1, lk rather. Does anyone see the stupidness behind this again? You don't even have to use Zygmundi. It's the same idea, guys. Like exact same. Yeah, exactly. LK is going to be AKD, roughly. And that doesn't work. Because see, you have to remember that LK is a sequence of integers. That's the thing that helps analysis with limits. See, if I have a limit of real numbers, some f of x, let's say I find out g of x, such that limit of x tends to infinity, g of x is equal to 2. So does that mean g of x is 2 for large enough x? Obviously not. Take 2 minus 1 by x. But if I say that g only takes integer values, then it will reach 2, no, because integers are discrete. They will change by plus 1, minus 1, only integers. They won't take all values in an interval. They will only take split points like this. So if it limits to a certain integer, it must become that integer after some point. Because there is no sense of arbitrarily close to an integer.
Yeah.
Get it? So it's the exact same idea again. Because this must hold for all d, it follows that LK must be KD, which instantly forces d equal to 1. Done.
Yeah, or we can expand the LHS also.
Okay, so
So then, if we
after you
remove,
know LK equal to KD or before that?
no, before that,
Okay, so you expand it, all right? You get
and
some binomial theorem stuff. Okay, equal to
yeah,
b to the power
and
LK plus 1.
one cut out,
Yeah.
and then we cut the highest power of B from.
Yes, exact same idea. Huh. So like I said, this is pretty much the same idea, right? You're just using it differently now.
Yeah, yeah, same idea.
So it's the exact same idea. We're just using it in a more different way here. The same VB idea or the same size idea. Remember, these are not identical. VB is more diverse. It can do other things, and this size can do other things. It's just so that here they achieve the same thing. It doesn't mean they're similar in all ways and in every context, but here they can help you achieve the same. Okay. So anyways, what does this tell us? This tells us b is 1. So what does that tell us about the original f of x? It's equal to b to the power
B
L
to the
times
power
x.
C times X. Yeah.
Yeah, L, this is L. Okay. So, and this obviously works. This works because you just have 0, 0, 0 at the end. Sum of digits remain same. So yeah, this finishes. Does everybody understand how this works?
Yeah.
Okay. All right. Now let's go with 7 because that was the second most popular option. All right, Debayu, can you put 7 up, please?
Maybe we can do like a problem made by a certain someone instead first.
Oh, all right, all right. Post that one then. Okay, we'll get back to 7 right after this one.
Okay, so
I think some of you may have seen this before.
yeah, this is a very famous problem. Okay, you have 5 options of
I
like
think
who.
Mayuk should remember.
Okay, guess the proposer. Is it Evan Chen, Nikolai Beluhov, Anant Mudgal, or me, or maybe someone else?
Those were very random options. Like just
So the correct answer is not Evan Chen, and neither is it. It is Nikolai. It's actually our Archit. How surprising is it? Okay, it turns out it's not that surprising.
yeah. I mean, this. I think some people have seen the problem before, so it's not that surprising. But yes. So okay. So let's try this problem.
Also, just a note: 0 is like a perfect square.
Yeah, 0 is treated as a square here. So x square is to be treated as a sum of 2 squares because a square and 0 square, x square and 0 square. Okay, does everybody understand what the problem says? The problem first says, okay, first a number can be written as a square plus b square, right? If good, if exactly one of I and p of I can be written in this way. So if I have p of a square plus b square, then it should not be equal to any c square plus d square. And if I have some p of some, let's say x equal to c square plus d square, then x should be of the form, x should not be of the form a square plus b square. Okay, wait, no, I just said the contrapositive. It's the same thing. Sorry. It should be the negative of the statement, which is p of x. Like it's an if and only if statement. So p of a square plus b square is not like this, and p of something which is not like this is going to be like this. Basically, if I have some x is not of the form a square plus b square, then p of x is of the form c square plus d square.
And also the problem has 2 parts. First,
Yeah, the problem has 2 parts. The first part says, can I construct a p? Does there exist some p which is I good for all 1 to n, like all 1 to n, this condition is satisfied? And does there exist a polynomial which is I good for all I, like for all I to n in n? So you have to show that there is such a polynomial, and then is there a polynomial which is good for everybody? Okay, what do you think the answer to the second question is?
No.
Yeah,
Right.
obviously, because if it was yes, then you would just keep that as an answer for proof for any positive integer there exists some p, right? It would just automatically work for all positive integers n as well. So why would we ask a part 1?
Can't we just use interpolation for part 1, like take some if I is
Okay,
such
good
that
idea. But remember, interpolation, as you remember, let's go back to interpolation. In fact, where is interpolation? Let me zoom out. Okay. Yes, interpolation is all the way here. Yeah. So if you remember, interpolation simply produces a polynomial. It does not guarantee anything about its coefficients. Here, the coefficients are not necessarily integers.
yeah, okay.
Observe that. So if I were to interpolate over here, like I randomly select the matlab p of from 1 to n, I select p of 1 is not going to be of the form a square plus b square. P of 2 will be of the form. I randomly select some numbers and I say I will interpolate over these. It will produce some p, but p will have rational coefficients. It will not have integer coefficients. Here I want integer coefficients because it's in z of x. Is it okay if the class extends for say 15 minutes?
I hope it is.
Yeah. Yeah, all right. Fine, great. I think people are fine with it. Thank you.
Yes, sir. Guess who made it? Any ideas?
Okay, part 1 is actually very stupid. So, okay, before I go into this problem and its solution, there is a prerequisite all of you must know. It's about when can I write a number n as the sum of two perfect squares? When can I do this? When can I find a and b integers such that n is equal to a square plus b square? Like, what special property does n have to have so that I can do this? This is the first question we must ask. You're saying it can't have 3 mod 4 factor. I don't think that makes sense. For example, let's say I selected let's say I selected 36. Say, 36. 36 has 3 as a divisor. 3 is congruent to 0, and this is 6 square plus 0 square. Correct. If A and B are co-prime, then but I don't care about A and B. I don't even have A and B with me right now. How can you argue about A and B being co-prime or not co-prime? I only know N, right?
It's
Yes.
the sum.
Correct. N cannot be 3 mod 4. So what does that mean? Anything not 3 mod 4 works.
The thing is, if the GCD is like 1, you have no 3 mod 4 factors, and you should have like a similar restriction on the 3 mod 4 primes if it's like if the GCD is
Yes, exactly. Pyro has found the correct answer. It's basically all primes P which are congruent to 3 mod 4. For those of you who are wondering why 3 shows up, I'll just brief you on why that happens later. So for every prime that is congruent to 3 mod 4, VP of n must be even. Do you understand why? I'll prove why this is. Because VP of n is, say, suppose it's odd, right? So let's say I have p to the power 2l plus 1. Now p to the power 2l plus 1 divides, let's say I wrote it as a square plus b square. P to the power divides a square plus b square. Correct? Then, by what he said, P must divide both A and B, because if A and B were co-prime, then it would not work out, right? So P must divide both A and B. So P divides both A and B, so I can remove P square, I can factor it out from here, and I'll get some A by P, which I'll call A prime squared plus B prime squared, right? And here this 2L plus 1 becomes 2L minus 1. Then again, I notice, okay, again, P to the power 2L minus 1 divides A square, A prime square plus B prime square. And again, I remove a P square factor and I keep doing it. And at the end, I'm left with P. And I have P divides A square plus B square. Now, at this point, again, A must be divisible by P and B must be divisible by P as well. And then I get P squared out, right? But there was only P left. You don't have more prime factors because VP is the maximum prime dividing. Does that make sense? That's the maximum prime power.
Yeah. But how
So-
can you show that P divides A square plus B square implies P divides A and P divides P?
Yes, that follows from quadratic reciprocity. Okay, this is not, I don't even have to go into quadratic reciprocity. It's just Fermat's little theorem, just scaring you for no reason. But okay, let's say P divides A square plus B square. A square is congruent to negative B square modulo P.
Yeah, using orders.
Right. Yeah, now take P minus 1 by 2 power, both sides. So what do you get? You get A to the power P minus 1 is congruent to negative 1 to the power P minus 1 by 2 times B to the power P minus 1 modulo P. Right.
Yeah.
Now, if P does not divide A, then obviously P also does not divide B. And these two are 1 modulo P. So I get that minus 1 of P minus 1 by 2 is congruent to 1 mod P.
Yeah.
Which means that P minus 1 by 2 is what?
Even.
Even. What does that tell me? P is congruent to
1 mod 4.
1 mod 4. But P was congruent to 3 mod 4. This is a contradiction.
Yeah.
Okay. Yeah. So that's why 3 mod 4 exists. Now, anyways, forget this is just details. So now we have a characterization for when we can write n as a sum of two squares. It is precisely when for all primes P congruent to 3 mod 4, VP of n is even. Okay.
But can we show that any number of this form can be written as sum of two squares?
Yes, we can. How you do that is, first of all, see, if some prime P of this form you have P to the power, let's say I have some prime P congruent to 3 mod 4, then P to the power 2e is there, right?
Yeah.
So I can just give A P to the power E and B P to the power E, and I can just get rid of this now. And then I can just multiply with P to the power E in the final answer.
Yeah.
Yeah. So I can just get rid of all primes congruent to 3 mod 4.
Yes.
So now I'm left with a bunch of 1 mod 4 primes.
Yes.
Now comes the most important part. This is what I will not prove because it takes time. You can write every prime P congruent to 1 mod 4 as the sum of two squares. This has multiple proofs. There's a pigeonhole proof using something, I believe it's called Thew's theorem, but I will not prove it here. But you can express any P congruent to 1 mod 4 in this form. Okay. And
Also,
just
we
observe
can
this
take
identity
order
to
of
finish.
AB inverse.
Is it again? I do believe it's this. Did I get it right? Yes, I think this is known as Lagrange's identity. How many of you are familiar with this? Do you see how this identity helps you in finishing? Because see, your number, it can be written as the product of a bunch of congruent to 1 mod 4 primes now. Some product. Each one you can express this way and just start multiplying and using this repeatedly.
Yeah.
And then in the end, you'll get a bunch of sum of two squares. So the main important thing you need to know here to be able to prove this is this part. This is the only, non-trivial fact here. Everything else is fairly easy. Okay. Now that we're done with this hard prerequisite, now let's go into the actual problem, the actual polynomial stuff, Okay. Let's go here. Okay. So yeah, now we can answer when n is of the form a square plus b square. When VP of n is even for all p congruent to 3 mod 4. Okay. Okay. Now let's come back to the problem. The problem says f of I, exactly one of these two is good for all I, not all I, for all I in 1 to n. Then that's the first part of the problem. Okay, does anyone have any ideas how we can construct stuff? The hint is it is similar to Lagrange interpolation, but it's not exactly interpolation. Like the ideas are there, everything vanishes, but it's a bit more, what can I say? A bit less ugly. I'll give you two observations which will help you finishing. The first observation is x square is always of the form a square plus b square, trivially. Second observation is 3x square is never of the form a square plus b square. Can you prove both of these? Okay, say the first one. Can you show that any x square can be written as a square plus b square? Come on, this is trivial.
X square is of the form 4k or 4k plus 1.
No, that is not again. Again, remember the condition. The condition states this. VP of n is even for all p congruent to 3 mod 4. It's not about 4k or 4k plus 1. I can give you example of 4k plus 1 which don't work. For example, 21. 21 cannot be written as a square plus b square, even though it's 1 mod 4.
Yeah, so like it would always be even because it is a square number.
Yeah, or I don't know why nobody said this. A equal to x, b equal to 0. Yeah, come on. Remember the original definition. It's sum of two squares only.
Sorry.
Okay, I'm going to excuse you there. Now 2. Let's do 2. Why is 3x square not expressible in this way?
Because 3 is congruent to 3. I mean, x square has all the...
Correct. X square has all even
and 3 is of the form 4k plus 3.
Exactly. Very good. That works. So 1 and 2 we have proven. So now just by using these two, we can construct such a polynomial f. But how? Okay, and let's take an example. N equal to say 8. 8 won't be computationally intensive, so I'll just do this. 1, 2, 3, 4, 5, 6, 7, 8. Let's go one by one. Which ones can be expressed as a square plus b square? And which ones can't be? Wait, I ended the brackets too early. This will probably be bigger than this. Yeah, okay. So is 1 of a square plus b square or a square is, or if it is it not of that form? Can 1 be written as a square plus b square or not?
Yeah.
Right, so we'll put 1 here. Can 2?
Yeah.
Can 3?
No.
Okay, someone says 1, 2, 4, 5.
Oh yeah, 1, 2, 4, 5, 8. All right, I'm going to trust you here. Okay, and this is 3, 5. No, sorry, not 5. 3, 7. That's it. Right. Yeah. So 3, 7. Now what do we want? We want f of 1, f of 2, f of 4, f of 5, and f of 8 to be not of the form a square plus b
No.
square.
Yeah.
So I'm going to say you can construct something such that when you evaluate at these points, it is of the form 3x square. And when we evaluate it at these points, it is of the form x square. Will such a polynomial work, first of all?
Yes.
It will work, right? Because when I evaluate it at a square plus b square, it will give me something which is not expressible that way. When I evaluate it here, it will give something which is. So now think of ideas. How can you come up with something like this? The construction is so simple, you will probably be angry. Okay, I think I'll just tell you. Do you see where I'm getting at?
Okay. So
Do you see why this works?
yeah.
Because when I evaluate it at this, in for this set, it just becomes 0, this part, and this part becomes of the form 3u square. And when I evaluate it here, it just becomes u square. Done?
Yeah.
And does this work for any possible integer n?
Yes.
Obviously, because I'll just create these two lists and I'll just create my polynomial like this. Okay.
Yeah.
So that finishes the first part of the problem. Now let's move on to the more interesting part, which is part 2. Can we construct a polynomial such that this holds for everybody? Like for everything f of I and I, exactly one of these two can be written as a squared plus b squared. Like somebody already said, the answer should be no, because otherwise the problem is useless. But how do you show that? See, this problem might look scary, but actually very easy. So like, for example, like part 1 might seem like the construction is like something very, very smart, but it's really not. It's just some ideas. That's it. Oh, and yeah, by the way, note 3 can be replaced with any number which cannot be written as in the form a square plus b square. Any number works. So I could have put 21 here also. Doesn't matter. Anything works. Anyways, this.
Okay, as I mentioned earlier, 0 is also a perfect square. So suppose we have x squared.
Yeah, so consider f of x squared. What is special about this number?
Yeah, it cannot be a square plus b square.
Sorry,
It cannot be a square plus b square.
correct. So
So it should be
what does
of the
that tell
form
us?
4k plus 3.
Again, that is incorrect.
What do we know
No.
about like the
BP should be of 4k plus 3 should be odd.
Yes, so there should exist a prime p congruent to 3 modulo 4 such that Vp of f of x squared is odd, right? Because if it was even everywhere, then you can express it as a sum of two squares,
Yeah.
right? So it's odd at some point.
Yeah.
Let's say it's 2k plus 1, as is already written. P of 2k plus 1 divides f of x squared. Now the idea is basically to use standard stuff. M minus n divides P of m minus P of n. Is it not?
Yeah.
Here we'll take m minus n equal to this. So P to the power 2k plus 1 also divides P of x squared plus any L times P to the power 2k plus 1. Right?
Yeah.
But can we really say that P of 2k plus 2 does not divide this? Can we say that? See, we knew about, sorry, this is F. We knew about Vp of f of x square that it is exactly equal to 12 plus 1. Can we say the same about this?
something must go wrong when the new p is larger. But what exactly goes wrong?
Look, if p to the power n divides m, does it mean that Vp of m is equal to n? Just a general question to everyone. Oh yes, Pyro has come up with the correct answer. If P divides L, then we can say that. Very good, very good. If P divides L, then we can say that. In other words, if we make this 2k plus 2, then we can say that. Why? Because P to the power 2k plus 2 divides the difference, right? It divides the difference. This one is something like P to the power 2k plus 1 times some U, which is not divisible by P, and minus some L, not L, or V. Let's choose V. Okay. This, what does this tell us? This tells us that V is of the form P to the power 2k plus 2 times some number n minus 2 to the power k plus 1 times U. Or actually opposite, I think. It should be this negative and this positive. Right? We get this? I sense some misunderstanding over here. Let's try again. We have f of x squared, and we said Vp of this is odd for some prime p congruent to 3 mod 4. Let's just write that here. This is equal to say 2L plus 1. Now I'm saying pick x square plus, let's take a small number, say 2. 2 times the power 2L plus 2. Okay. All right. We know, consider this f of this. Okay.
Yeah.
So this quantity, what is Vp of this?
2l plus 1.
Why?
Because if it isn't, then
Yeah, because we've added a multiple of
yeah,
2l plus 2. So that won't affect because this is still 2l plus 1, right? This is one step below. So even if I add something, even if I add p to the power, let's say, something much larger, l to the power l also, it will still only remain 2l plus 1. Because when
Yeah.
I remove this small thing out, I'll be left with something large, which is divisible by p, plus something, no matter how small, it is still not divisible by p. So the sum is also not divisible by p.
yeah,
Okay, so VP of this is also 12 plus 1. Here comes the final, final thing that will kill the problem. What does this tell us? We know that VP, P is congruent to 3 mod 4, remember. And VP of this is odd, which means that this number cannot be expressed as,
x square plus y square.
yeah, a square plus b square, exactly. Which means that from the problem condition, the inside value, what can we say about this from here? This can be written as a square plus b square, right?
Yeah,
Because exactly one of those two should be expressible. And because f is not, the other one must be.
yeah.
So this definitely is. Now how can we finish? By the way, remember that 2 was just chosen for example. So 2 is in fact anything. So we can even make this some k, just to remind you. So basically we know that for all k, this is of the form a square plus b square. Oh yeah, someone says, oh yes, 2 already works. Yes. X square plus 2 times p to the power 2l plus 2. This is 3 mod 4. Why? Is it really 3 mod 4? Why is x square 1 mod 4? Yes, exactly. We can pick x odd. So from the starting, we could have said pick x odd because that is up to us. So we say x is odd and we just take 2. So this quantity is congruent to 3 mod 4.
Yeah, so one of
So it
these
cannot be
prime
expressed as a
factors.
square plus b square,
Yeah.
which is a contradiction because we should be able to do it.
How did you come up with the problem?
To be frank, I don't remember anymore, but I think it was originally with some interpolation stuff. And then someone asked me, why can't you construct polynomial which works for 1 to n? And then I started working on that problem. And then once I found that, okay, yeah, you can't construct anything like this because of so and so proof. Initially, my proof was along this only, but it was much more complicated. Like I had complicated a lot of things, but this is a cleaned up version. In fact, an even more cleaner version would be just pick x equal to 1.
So like in general, these polynomials which like satisfy exceedingly nice properties don't end up existing because like it's just too much constraints. Like the first problem we looked at, which is like p of n is rad of n time like to the power rad of n. This is just too good to be true. So it's a natural question to come up with that if that a polynomial just might not exist if such very nice conditions are satisfied.
Actually, the second part of the problem was suggested to me by Vlad. And then I worked on it and then I found that, okay, yeah, it does work. Like, as in, does work in the sense that no, there is no such problem. Anyways, enough about this. Now let's finally just go with 7 and get everything done with. All right.
Wait, the N6.
I think we don't have time for N6.
It's so nice though.
Is it?
Okay, do people want to do the N6 or P7? The N6 is like the best problem.
I think he's overinflating the niceness of that problem.
Yeah, isn't that?
Okay.
Please pick one of the two problems. The N6 is like very, very nice. The idea is just so good.
Is it?
It is.
It's honestly a bit debatable.
What?
What?
I mean, is it that nice?
Who is this? This is him.
Wait, you were Atul all along.
Oh yes, must be this.
Pyro is up there. No wonder. You know, it's not surprising. I was.
I thought he was like Bravo.
I just thought it was a random person. Wait, so that means the guy messaging. Okay.
Yes.
Concerning behavior. Okay. Ignoring that, let's do
The N6.
no, we're doing 7. I think 7 was second voted. Nobody voted N6 as far as I remember.
No, we just voted for those two problems. That's why no one voted for N6. The N6 was in the other page.
No, I don't know. Like I only hear the fact that there were 0 votes.
Bro,
Okay.
just tell me, isn't this statement like magical? Okay, not magical, but fine.
Okay. Let's go with this. We have to find all polynomials f with integer coefficients such that f of p divides p minus 1 factorial plus 1 for all primes p. Ideas? Anyone? Okay, how many of you have heard of Wilson's theorem? Some I'm sure you have. Okay, so Wilson's theorem basically states that for all primes p divides p minus 1 factorial plus 1.
Notice that a lot of stuff is like coplan with f of p.
Yes. So, like, as an example, I think a general idea when you're attempting any problem involving polynomials is just take a random value. Like, say, I pick some p such that f of p is positive, perhaps. I can replace f with negative f if this never happens. So I just pick something like this so that it's greater than 1, sorry. And I just analyze all primes q that divide f of p. Okay. It makes no sense to like think of f at points other than primes because we are only like given condition over a prime. So let's just restrict ourselves to primes right now. So we have q divides f of p. Now what? This divides q minus 1 factorial plus 1. So what does this tell us about q?
Q is greater than P.
Yes. Q is what? Sorry, could you come again? Q is
Greater than equal to P.
correct, greater than equal to P. All right. Now what? Now see, try to remember the fact that if Q divides f of P, then Q divides f of P plus KQ as well. For any K.
Yeah, so
Now what?
Dirichlet theorem.
Yes, correct. P plus KQ can be forced to be a prime, say R. So you get Q divides f of R, which divides R minus 1 factorial plus 1. By the way, you can only do this when Q is strictly greater than P. Not when Q is P, obviously. Then you can't say stuff like this because then these two are no longer coplant. Anyway, so you get Q divides this, which means you get what? Q is at least R, which is
Yeah.
nonsense because by Dirichlet, there are infinitely many such R.
Yeah.
So
In
for
this-
each f of P, the only prime dividing it is P,
Yeah, but
which means that each f
impossible.
of P is equal to some P to the power XP.
Yeah.
Now do you see the finish? We've done this over and over. Oh, sorry. Yeah. P to the power XP. Yeah. This is for, let's say, large enough primes, P greater than or equal to, say, M. How do we finish now?
Also, if you don't know what Dirichlet is, it just says that if you have an AP
Dirichlet, my bad. Dirichlet says that AN plus, go ahead.
and GCD A comma B is 1, then you have like infinitely many primes in this sequence.
This is an arithmetic progression, by the way. So basically, any arithmetic progression you write out, it'll have a lot of primes in it, as long as, obviously not something divides everybody. Anyways, how do we deal with this? I mean, we're practically done now.
Come on, this is not too hard. You have done.
We've seen this before as well, guys. Remember when we did f of b to the power k is equal to b to the power uk? It's quite similar to that. Okay, I think I'll just do this now because So again, same stuff, fx over cx to the power d, limit x tends to infinity is 1 for some CD. Now just do this over the primes. So limit p tends to infinity, f of p, which is just p to the power xp over cxp is equal to 1. Again, c goes there. You have what? No, p to the power d. Let me clean this. By p to the power d is equal to c. So xp minus d limits to constant. It will in fact become 0 because it has to be equal to 1. It's bounded. So this is 0. That we are dealing with, and c for equal to 1 follows directly after, and then we get f of x equal to x to the power d for some d for all x, because it's a polynomial and this holds for large enough primes, it holds for every x. Now just observe that f of 2 is equal to 2 to the power d say, and this is supposed to divide what? 2 minus 1 factorial plus 1, which is just 2. So d is at most 1. From here it follows that f is either constant 1 or plus minus x. Well, only plus x here because we already did f2 minus f earlier, remember? So we have 1x, and then we also get -1 and negative x because we did f2 minus f earlier. So all solutions are plus minus 1 and plus minus x. Those are the only 4 solutions to this. And all of them work, as you can check. They work due to Wilson's theorem. Yes, so I guess that's it. Yep. I think we discussed quite a few problems, as you can see, like all of them featured some or the other idea, which you can, I guess, take away.
And 2011 and 6 is a homework.
Sure. Like I won't force it on you, but like if you like the statement, go ahead and try it.
But I
Not
won't
bad.
force it on you, so you must do it.
Okay, I think we can end the class now. How do you end it? Not sure. I think
Don't.
Yeah, I will end it.
Yeah, just end the screen share and he will stop recording.
all right.